All right, so we are going to spend today in lecture as well as in lab time, and Tuesday as well in lecture and lab time, basically going over the basic chemistry concepts that we are going to be using as a foundation to build on for this whole semester. And I would request, if people are not currently talking, to mute themselves, because it ends up bleeding through, and then I can hear, everybody else can hear it. Cool. Let's see. All righty then. So I'm going to share my screen here. Oh, not my screen. Share whiteboard. There we go. Okay. So the chemistry concepts in this class are, they're the fundamental things. Like, we're not going to have you decide which particular orbitals are getting filled up as you are looking at a particular atom or this or that, or is it 1p or 2p or blah blah blah, but we do, there's no 1s or 2s or whatever. But we do care that what valence electrons are. We do care, you should know the things in the first column of the periodic, in fact, if you look at a periodic table of the elements, this should not look scary. This should look like, oh yeah, I know this thing. What determines what a particular element is? How do I know if something's a lithium or a chromium or a titanium or an oxygen or a neon or a carbon? What is the defining quality that makes an atom one particular element versus another?
How many protons it has?
Yeah, exactly. How many protons are in the nucleus? Yeah, Sienna, I actually saw your hand up, but because, I think just being vocal is probably best in the Zoom world. In a normal classroom, raising your hand is the polite, correct thing to do, but in Zoom, you just get lost. Yeah, so, the atomic number, that number at the top there of each of these squares, that's how many protons is in the nucleus. And no matter what else about this thing, no matter how many neutrons, no matter how many electrons, the element is going to be defined by that number of protons. If an atom is electrically neutral, it's going to have a matched number of protons and neutrons. So if I have a sodium, in fact, let me go into my annotate dealy bopper here. If I have a sodium and it has 11 protons, that makes it a sodium. If it's electrically neutral, it would have 11 electrons. But pretty much everything in this first column, these alkali metals here, these all have a single valence electron, one electron in their outermost shell. These tend to ionize pretty immediately. Once you put them in water, they're going to lose, and pretty much everything we're looking at in this class is in an aqueous solution. So if you put sodium or potassium in a situation where there's other stuff around, that valence electron is going to just disappear. So if I have an electron that gets taken off of an atom, what happens to it?
It becomes stable, right? Because it has the 8 on the outside.
I would say it's energetic, more energetically, the whole octet rule, but let's think more about something major is happening. If this isn't about completing.
Does it become ionic?
Sienna? Yes. Actually, Sienna said it first.
Becomes an ion, yeah.
It becomes an ion, becomes an electrically charged atom. So if a sodium or a potassium loses an electron, it is now, we'll write it as, Na plus, or as potassium, K plus. I wouldn't, it's going to want to interact because it's highly charged. So it's going to get either pulled towards opposite charge or pushed, repelled from. So it's, the octet rule that someone was just mentioning, when we talk about covalent bonds, that's going to be important. Kind of that most stable, energetically stable configuration is when the valence shell is filled. These things in the second column here, in particular, the ones we're going to see are magnesium and calcium. These have two electrons in their valence shell, which means when these are in water, they're going to ionize, but lose 2 electrons. So what's going to happen there?
It will become like magnesium 2+.
Exactly. It's going to become magnesium 2+. So when we talk about magnesium, you can either write it like that, or you can write it with, 2+. Calcium as well will be a +2 cation. So these are going to be incredibly important, these ions. I'll talk about them in a little more later, but these ions, whether they're sodium ions or potassium ions or magnesium ions or calcium ions, are the main charge carriers for all the electricity in your body. Like the electricity in the circuits in your iPhone or in the computers or in your toaster, those are mainly electrons that are carrying charge to make electricity. But in your body, you're going to have a flowing of ions. So it's going to be really important to have a good sense of ions, because those are going to be moving to create the electrical currents in your body. Separation of charge is what voltage is. We're going to be separating positive and negative ions to make the voltages across membranes. And again, we're going to talk about this all in more detail, but just at the core, knowing what an ion is important, because ions are at the core of all this electrical activity in your body. If you go into this, what are these? These are the halogens. These things here in this column, this second to last column before you get to the noble gases, these all have basically 7 electrons in their valence shell. And for them to be most energetically happy, they're going to grab an extra electron and fill it up. So like particularly, we'll see mainly chlorine. If I have a chlorine and it actually snags an extra electron on top of what it already had, what is going to end up, what are we going to end up with?
Chlorine minus.
Yeah, I'll end up with a chlorine minus. So let me get back to my whiteboard now. So basic idea, if I think about different atoms, I have this nucleus. If somebody, it's being recorded. I have, after spazzing a few times in the past, I have it so it automatically records when you start the session. So I can't forget to record it ever again. So a nucleus of an atom, again, this should not be a surprise. Protons and neutrons. And then, in some probability density function cloud around the outside, we're going to have the electrons. Again, the number of protons, that's what we call the atomic number. That's going to determine what element it is, right? So if I have 19 protons, it's a potassium, no matter what. If I have 11 protons, it's going to be a sodium, no matter what. If I have 17 protons, it's a chlorine, no matter what. Protons are also, positive charge. The neutrons, we care about the neutrons, but not that much in this class. Depending on how many neutrons, this atom is going to be stable or not stable. In fact, in a medical context, the main reason we care about neutrons is there are certain, in fact, what do we call, if I have a version of, like I can have sodium, again, if I have sodium, actually I should just say sodium has 11 protons, and I can have sodium with 11 neutrons, or I can have sodium with 11 protons and 12 neutrons. It's actually, both of them are common. What do I call those two different versions of sodium?
Isotopes.
Isotope.
Yeah, those would be different isotopes. Different isotopes. They're still sodium because there's 11 protons. That's all that matters for it to be a sodium. It'll have a different weight since neutrons weigh about the same as a proton. One of these is going to have an atomic mass of 22 versus 23. But they're both stable. Some isotopes are not stable. The nuclei break apart and you get radioactivity coming off, which is actually useful in medical imaging or in cancer treatments like gamma knives or something. You want radiation to kill some tumor cells. So there are radioactive isotopes for imaging and for cancer treatment and stuff that are actually medically relevant. But for our class, you should know what an isotope is. Isotope is just a version of an element with different numbers of neutrons. But for the purposes of our class, we're just going to be thinking about stable isotopes. So you don't really got to think about it beyond the definition. Number of electrons around the outside. Again, electrons, I'll usually draw them as an E- because they're an electron, which is an E, and they have a negative charge, so the minus. Again, if I have, something like, sodium, which has, 11 protons. If I have, and if I look at the valence shell, it's only got kind of one lonely electron just out in the very out part, which tends to ionize. So then I'm left with only, 10 electrons on the outside here, which means I'm going to end up with an Na+. Right, and like I said, pretty much all the sodiums we are going to be thinking about are going to be Na+. Same thing with potassium. Potassium is going to be potassium plus. Calcium is going to be divalent cation. Magnesium will be 2+. And again, we can write this also as like Ca2+. I should also mention, we are going to be using sodium and potassium so often in this class. And the shorthand is from the Latin, obviously natrium, not sodium. So if this is not like just triggering instantly in your brain sodium, if you're seeing an Na, you want to get there. I'm going to be writing Na plus and K plus on the board or on the white, whatever this is, so much over the next 4 months. You definitely want to know that like that K and that Na should just instantly be triggered in your mind that it's a potassium and a sodium. You shouldn't want, initially you might be translating it more in your head, but eventually it's just instant. Things like Ca for calcium are a little easier. If something becomes a positive ion, then it's called a cation. So cations like sodium, potassium, calcium, magnesium. Other common kinds of ions, like I said, are the ones that are from that second to last row or column in the periodic table. And specifically, chlorine is the one we'll look at. Chlorine is going to have 17 protons in the nucleus. It usually wants to grab an extra electron to complete its valence shell. So it's going to typically have 18 electrons, which means I'm going to end up with a Cl minus. So if I have a negative ion, that's called an anion. What else? We can, I don't know if it helps. Like, I know, like for me, having kind of stupid, nerdy jokes was actually useful. Like, the sodium like walks into the bar and he's like all like freaked out. It's like, oh, I lost an electron. I lost an electron. And like the bartender, are you sure? It's like, I'm positive. So you can like, if that helps you remember things. But definitely ions are going to be at the core of all the electrical stuff. Let's talk about electricity, or I say electrical current. Electrical current. This is just flow of charge. How many amps are, you've probably heard of amperes, milliamps. That's just flow of charge, how much charge is flowing. And again, in most of the electronics you're used to, the flow of charge is the flow of electrons, usually through metal. But in your body, it's going to be a flow of ions through an aqueous solution. And it still carries electricity. It's what electricity is. You're still complete a circuit. You can still light up a bulb or make a buzzer go or what. In fact, you're going to see we can use ions in water to complete circuits and make buzzers buzz in our lab next week. It's going to be the way we can tell if the solution is conducting or not. So electrical current is flow of charge. I should say electrical voltage. This is also electric potential. Is separation of charge. I can try to describe this briefly. We'll look at this in much more detail. So if this is confusing right at this moment, don't get too concerned. But imagine I have a preponderance of plus on this side and minus on this side of some boundary. I now have this electric field, this gradient. So it goes from more positive to more negative, which means that if I take an ion and I put it in this particular scene here, that ion is going to actually get a force on it. So if let me take let's take a potassium, a K plus. I'm trying my best to use my little system here. So here's some K plus, and I'm going to cut it. Now I can move it. If I put it around here, which direction is it going to, what side of this boundary is it going to get pulled to?
Negative.
Negative.
Exactly, opposites attract. So this electrical voltage, this electric potential means if I take a cation like potassium and I put it in here, it's gonna get pushed away from this side and pulled over to this side. So, potential energy is like there's something waiting to act and create this kind of force here. So here, this is an electrical potential that's caused by a separation of charge, right? If it was just homogeneous, just plus and minus equal everywhere, this K plus would not be pulled in any direction or another. It would just be wherever it is. But electrical voltage, the separation of a charge, typically it's on either side of a cell membrane, is going to make this ion want to get either enter or leave a cell based on the direction of the charge separation. So that is going to be an important concept as we continue on in this class, is this idea of electrical voltage, that if you have a separation of charge on one side or another side of a membrane, and then you look at what does an ion want to do, this ion is going to go towards the opposite charge. And again, these pluses and minuses that I'm drawing here, they're basically ions. Here I've got more anions. There's more chlorides than the cations. On this side, I've got probably more potassiums or sodiums compared to the other side. So when I'm drawing these pluses and minuses, I'm actually talking about ions, these charged atoms. So, okay. So that's kind of the atoms. We are going to talk about how we assemble atoms into molecules in a little bit through all the bonding. But first, I want to take a little detour into the other part of chemistry, which there's energy and matter. We're talking about matter, but let's talk about energy briefly. And then again, we're going to return to the atoms. Okay. And again, matter can be solid, liquid, gas. And there's other phases that we're not worried about in this class. Energy takes up many different forms. And that's going to be important for us to think about the different forms of energy. And again, energy is like the ability to do work. What are the two fundamental divisions or two fundamental categories of energy?
Potential and kinetic.
Yeah, there's potential energy.
Is the other one
Versus-
stored or active?
Kinetic.
Called kinetic. Kinetic, this is the energy of motion. So anything that is currently moving has kinetic energy. It's like 1/2 mv squared is the formula if you've been in physics. But basically, if I have, I don't know, here I have this stapler moving, and then it hits it has the energy to create a whack and a sound. So anything that's moving has energy, and the energy is based on its mass, it's based on its velocity. We will be seeing kinetic energy, but that's not what I want to focus on right now. I want to focus on the potential energy. And this is stored energy. This is energy that is stored. Nothing is moving. Nothing's actually happening in the moment, but there's energy that's locked away that we can release. What are different forms of potential energy?
Food, fat.
So food and fat are examples of what kind, where is the energy actually stored in food and fat?
Chemical bonds.
It's stored in the chemical bonds. Exactly. So we have energy stored in chemical bonds, and when we rearrange chemical bonds, depending on what the reaction is, we can release that energy. Again, that is why your food gives you energy. You take the sugar molecules and you break them apart. It's basically combustion of glucose, which we'll look at in way more detail, and you release energy. You know, if you burn some wood in your campfire, it's the same basic chemical reaction. You're converting that cellulose in the wood into carbon dioxide and water and lots of heat and light, releasing that energy. So chemical bonds. Think about gasoline, the octane molecules. You put a gallon of gas in your tank of your car, and you can move a ton of steel 30 miles across the land. There's a lot of energy stored in a gallon of gasoline in those little molecules, right? So just this idea, chemical bonds store a lot of energy. And, you know, what's the one molecule, you know, we talked about, we're going to be looking at glucose a lot, since that's kind of the main thing you feed into cellular respiration. What's another molecule that we often use to kind of break apart to release energy?
ATP.
Yeah, ATP. Remember, ATP breaks apart to ADP plus an inorganic phosphate, plus it releases energy. You know, ATP, adenosine triphosphate, it's got 3 phosphates. This is adenosine diphosphate, so now it only has 2 phosphates left attached. The convention is if the phosphate is no longer connected to a carbon-containing entity, you put the little sub I on there, because it means inorganic phosphate. It's no longer connected to a carbon-containing thing. So, but ATP breaking apart into ADP plus phosphate and releasing energy, that's the thing that drives so many of the things we're going to be looking at in our cells over the next 4 months. It's also when we break apart the glucose, pretty much what we're doing is we're taking the energy stored in the bonds of glucose and converting it into the energy stored in the bonds of ATP, which is much easier to access and utilize in an instant way in all the cellular processes. But again, we're going to be spending lots of time looking at the breakdown of glucose, the creation of ATP, and all of that. But this idea, chemical bonds, super important in this class. Potential energy that's stored there that you can then release under the appropriate conditions with the appropriate reactions. Okie dokie. What are other ways to store energy?
Mechanical.
Totally mechanical. You know, classic things here would be like a spring, right? You take a spring and you squish it, but you hold it so it can't move. It's not going anywhere, but there's a lot of energy in that compressed spring. And when you let go of it, boing, it flies up and does something, right? Everybody's probably experienced a spring in their life. We're going to see mechanical energy even in a molecular level. Like you've probably, in fact, I know you've all seen it. You've all been in Bio 110. You know, the myosin heads in muscle contraction. You can take this little myosin molecule. Again, this is just a big protein, but you can like take the head and using the power of ATP, kind of cock the head, and then under the appropriate conditions, it'll spring and generate the contractile force in your muscle. And that's actually mechanical energy stored in this big protein, which then basically springs and pulls. We'll see other examples of mechanical potential energy as we continue. What are other ways to store potential energy?
Electrical.
Yeah, so Nikki was paying attention there, right? I just talked about electric fields. Right? If you have a separation of charge, you now have this potential energy that can work and push, move some ion one direction or another. So these electric fields are going to be important. Something that's related, but not exactly the same, are diffusion gradients. So let me talk about, I'll write it here, and then I will describe it more. So we should review again, what does diffusion mean?
What can pass the barrier, like right, like what can diffuse through?
That's more what we'd call permeability. Permeability is whether or not something can move through a boundary.
Going from higher concentration to lower.
Yeah, so this is movement from higher to lower concentration. And this is we call passive transport. You don't have to add anything to it. It's just a natural result of the movement or the energy of molecules in the world. So if I have something, whatever it is, some yellow thing, and there's a lot of them over here and not so many over here. In fact, let's just draw a boundary there to make it easier. Wherever there's a whole bunch versus where there's going to be a, yeah, I'm going to personify. It's not really, they don't have any intentions, or they're not looking around and deciding what they want out of life, but it's easier for me to think about it that way. So they want to move from higher to lower concentration. Wherever there's more of them, they're going to move towards where there's less of them. So this is a diffusion gradient. A gradient meaning there's a change from one side to another. So if there's a separation, this is not of charge now, this is just a diffusion gradient. There's more of a particular molecule here versus on this side. That's another form of potential energy. In fact, this is going to be a very common way for us to store potential energy in the systems we're going to look at. We push a whole bunch of molecules to one side of a membrane, and then they want to come back. Again, they want to come back due to the diffusion gradient pushing them back the other way. So this idea of energy stored in a diffusion gradient will be important as we continue through the semester. It's worth, I can talk of just a few moments about the reality of what diffusion is. So it's worth knowing what temperature is. What is temperature? If I say something's at a higher temperature or at a lower temperature, what is actually different about them?
How fast the atoms are moving?
Yeah, exactly. It's kind of the energy of all the little atoms and molecules that are in there. They have like vibrational, rotational, translational energy. They're all wiggling and jiggling and moving. So anything that is not at absolute zero is wiggling and jiggling and moving and flying through space. So it's important to realize, I'm saying passive transport, you don't have to add energy for diffusion to happen, but there is energy already there in just the things zipping around. And if you want to think about how does diffusion actually work, they don't want anything. But if you think about them randomly just zipping and bopping around, if this is, let's say this guy here is randomly moving that way, it's more likely to hit something because there's more stuff on that direction. And then it's going to bounce and change direction. Maybe it's going this way now. It's going to be able to travel much farther before it hits something because there's just less stuff over here. Right. So the idea of diffusion going from high to low concentration isn't so much about, again, I think about it, in a pretend way, like they want to move from high to low, but in reality, it's just they tend to move from high to low because if they're moving towards the higher side of the concentration, they're going to hit something and change direction. Whereas if they're moving towards the lower concentration, they're more likely to have a longer mean time of just going in that same direction before something happens. This is not an equilibrium. Like most of the stuff you've learned about in chemistry, most of the stuff we're going to talk about when we talk about the actual chemical reactions, we're going to talk about equilibriums. But this is obviously not an equilibrium. Things are imbalanced, and that's why they're moving. And again, you think about a bunch of kindergartners and they've all drank Red Bulls and eaten Snicker bars or something, and then you've just kind of just roped them all into one corner of a classroom, right? And they're just like, blah! But they, they're kind of high concentration right in the corner of the classroom. The rest of the classroom's empty, and then you cut them loose. They're not thinking like, oh, let's go from high to low. They're just like bouncing off everything, and they're going to start spreading out from high to low concentration. It's kind of like that. They just naturally are going to be bouncing around and are going to be drifting from where there's higher to where there's lower concentration. Diffusion will be important for the entire semester. We have 2 entire labs that just look at diffusion, and then osmosis, which is a special case of diffusion where we have the diffusion of water across a semi-permeable membrane. But it's pretty critical. So we'll be spending a lot of time getting used to diffusion, getting used to osmosis and all that stuff. So diffusion gradient is another form of potential energy here. There's one other kind of potential energy which is important in most things, but not so much in our class. Potential due to gravity. Right, if I take a, in fact, if I take a stapler and I do work and I lift it and against gravity, I have stored potential energy with respect to gravity, and I can drop it and convert that potential energy back into the energy of motion as gravity works and starts speeding, accelerating it downward. So for our, for our class, there is, gravity makes a difference in a variety of things, but it's not going to be as important as these other chemical bonds. Mechanical, electrical, and diffusion gradients are going to be the major places we're going to be seeing energy being stored. And often interconverted. Sometimes you'll take energy stored in chemical bonds and use that to pump things to create energy now stored in a diffusion gradient. Right, so we'll be seeing, like, in fact, that's what's going on in the mitochondria. When we look at cellular respiration in more detail, we're going to be seeing energy that was originally stored in the bonds of the glucose now becoming gradients of protons across the inner membrane of the mitochondria, which then can be tapped in to do yet other things. So it's important to keep in mind all these versions of potential energy. Okay. So any questions about energy? Okay, it's going to be a constant theme as we go through the semester. So now we're going to get back to matter. So chemical bonds. Right, obviously, if you want something more complicated than a simple element, you have to start connecting up atoms in different arrangements. Right, and classic, H2O. That's water. Start with something simple. Thing about chemical bonds, it's not just like two hydrogens sitting next to an oxygen. There's something more intimate going on. There's some, kind of, instead of exchange of bodily fluids, they're exchanging electrons or sharing electrons. There's something much more intimate going on when something creates chemical bonds or chemically bonded. We'll also have, when we're looking at mixtures and solutions, we'll also just see different molecules just sitting side by side, sliding past each other. But if we have atoms that are chemically bonded, there's something deeper going on. What are the two main ways to create different kinds of molecules using chemical bonding?
I know one's covalent.
So we're going to have covalent bonding
Ionic.
and ionic. So let's start here. There's going to be another kind of chemical bond that we're going to look at later, the hydrogen bonds, but it's more between different molecules or between different sections of a large molecule. But in order to kind of create the initial molecule, the initial thing, we're going to use either covalent or ionic. So let's look at both of them. So covalent. This is a sharing of electrons. So in this case, the basic idea is that octet rule, filling the valence shell of whatever. And water, you have oxygen. Oxygen has 6 electrons. It wishes it had 8. Hydrogen is kind of, instead of an octet rule, it has like a 2 rule because it just has a 1s. But it has 1 electron, but it wishes it had 2. And the way everybody's happy is they share. So we can have these 2 electrons here. This hydrogen sees 2 electrons, so it's happy. The oxygen now is seeing 8 electrons between all of these, so it's happy. And they all sit together. When they're chemically bonded, we use little solid lines in there to say this is now a molecule, and that these are no longer separate H's and O's. So that is a covalent bond, this sharing of electrons. I drew this as a kind of bent thing here, and that's because the electrons, the lone pair electrons, tend to actually push the protons of the hydrogens kind of down. So you actually get this thing that's not symmetrical. This thing that I've drawn here, this is what I would call a polar covalent bond. Because we have one side that is more positive, because these protons are down here, the hydrogens. We have this side here where we have the electrons, the lone pair electrons. So this thing, if you look at it from one side, it looks more, that's supposed to be a negative. One side looks more negative, one side looks more positive. Polar means it has poles, it has different sides. So it is not symmetrical. It doesn't come apart, it stays as a single unit. Overall, it's electrically neutral, right? there's no, it's not an ion. It has an equal amount of protons and electrons, but the distribution of the charge in space is not symmetrical. So one side of it is more negative, one side is more positive.
What does the S thing stand for? Like, is there like a definition for your positive and negative S thing?
It's a delta. It's just,
Okay,
it means that there's a difference in charge. Yeah, it's just the common way to write it down. So yeah, it's just my way of saying that side has a bit more positive compared to the other side, which is more negative. It's possible to have non-polar covalent bonds. You know, if I take methane, methane is taking a carbon and hydrogens. You know, in this case, the hydrogen each hydrogen shares with the carbon shares, the carbon gets 8, the hydrogens each get 2. The thing about this situation, though, is everything is totally symmetrical. There's no up or down or side or back to this thing. It becomes this little kind of tetrahedron. This would what would be called a non-polar covalent bond. There's no charge imbalance. So this is going to be super important as we get into water and aqueous solutions in a few moments. The idea that some covalent bonds are polar, meaning there's a charge imbalance. One side's more positive, one's more negative. There's going to be electrical attractions. Some covalent bonds are nonpolar. Everything's totally symmetrical. No matter what direction you look at it, no side of it is more positive or more negative.
is that because the H's and the oxygen or in the water are facing down? Is that what you mean by like not symmetrical?
Yeah,
Or do
it's
you mean the
because-
amount of electrons being shared?
No, it's the distribution in space. The fact that the lone pair electrons in the from the oxygen go up to one side of this thing and then kind of force the protons down to the other side of this thing. So one side, even though overall there's an equal amount of protons and electrons, there's more of the negative charge residing on this side, more of the positive charge residing on this side of this.
Okay,
So we're going to come back here in a few moments, particularly because water is is going to be super important. And water as a polar covalently bonded molecule is going to have a lot of implications about what happens in the aqueous environment in the body. So we'll come back there in a few moments, but actually let's go there now. Let's talk about water and then we'll get into the ions in a few moments. Yeah, let's do it now. So water. H2O, polar covalent. So again, if you think about an H2O, you have to think about it as this kind of a dipole. One side that is more negative, one side that's more positive. And then if I take a bunch of water molecules and I put them together, in fact, everybody has seen what happens if you put water in a glass. Do the water molecules just explode and go off everywhere, or do they sit together in a puddle?
Together.
They
Sit together.
They sit together. what is keeping water liquid rather than having the individual water molecules just to zip off and do their own thing?
Because they're attracted to each other.
They're attracted to each other, exactly. So if I take another water molecule, hold on, my little, the more negative side of this one is what, negative, is going to have an attraction to the more positive side of that one. And then I'll have another water molecule. And with the more negative and the more positive side. And again, the more, and I'm drawing kind of a dotted line now instead of a solid line, because this is not a kind of chemical bond like the covalent bond. This is just an electrical attraction. So this attraction, this electrical attraction, is what we call a hydrogen bond.
I have a question.
One moment, let me finish writing this and then I will answer you.
Technically, isn't there one oxygen? You've drawn it like there's the positive end of the two hydrogens. Is there not an oxygen attached to each of those hydrogens? Do you know what I mean?
I'm not sure what you mean.
Like how you have it coming off of only one hydrogen, the positive and the negative. She's asking if there's oxygen that comes off of one hydrogen and one off of the other hydrogen, or is it just one bonded to another?
No,
Yeah.
if you had H2O2, that's hydrogen peroxide. That's a totally different molecule.
No, I mean, with these hydrogen bonds, is there not a hydrogen bond between each hydrogen?
Oh, yeah, no, yeah, so I see what you're saying. Yeah, so obviously you could put little pluses. But for the most part, it's useful to just think about them as little dipoles. One side is more positive, one side's more negative.
Okay.
And I would think about it also, think about if you have a bunch of magnets with north and south and you put them in a bucket, the whole thing is going to go into a big glom because they'll shift around. These hydrogen bonds aren't necessarily all that strong, right? If you take water, you can splash into it and break them pretty easy, but they'll just reconfigure and find something else to grab onto. So when we have like water, liquid water, it's all of these waters all kind of holding on to each other, but kind of sometimes letting go and grabbing onto another one. So this is what water looks like when you have it as liquid water. It's a bunch of these little H2Os all kind of holding onto each other by hydrogen bonds. Let me be a little more explicit about hydrogen bonding, just because I mentioned it, I might as well be more explicit here. Hydrogen bonds. So one thing is they are not actually between atoms creating a molecule. These are, so attraction, so I'd say like attractions between separate molecules or between different parts of a large, actually very large molecule. So, hydrogen bonds are what kind of create the base pairing in DNA, when the A and the T hold on, but then you can pull them apart, but they'll snap back together. That's hydrogen bonding. We'll see hydrogen bonding happening in the folding of proteins. We'll see all sorts of hydrogen bonding. But hydrogen bonding is going to be critical for when a neurotransmitter binds onto a receptor on your neuron. But it holds on for a while, but then due to all the motion, it also can pull apart, right? Because it's not the same kind of thing like a covalent bond where there's this real intimate thing. It's more they're opposite charges kind of, and they're holding on, and then boom, they can break apart as well. So hydrogen bonds. And we talked about water. Let's talk about what happens when you put polar versus non-polar molecules in water. So here I have, let's draw some H2O. So here I am in, this is just a glass of water. These are obviously not all of the. So this is kind of what a glass of water looks like, or the inside of your cells. Most of your stuff is in water. If I take a polar molecule, let's say sugar. So glucose. Glucose is a polar covalent molecule. If we look at glucose, it's got, we'll look at this in more detail actually in lab. It's got oxygen in the ring, which has got those lone pairs. It's got hydroxyls hanging off, which are always a sure sign you've got charge imbalance. So glucose, we have glucose. It's got carbons, it's got an oxygen. It's got little hydroxyls hanging off of it. So it's got some parts that are kind of more negative, some parts that are more positive. So this is my glucose. My glucose is this complicated molecule that has some sections that are more positive, some sections that are more negative. What is going to happen when you put it in water? Sienna?
Possibly the positives will be attracted to a negative and it will split apart because the negatives will be attracted to a positive.
All right, so one, it's not going to split apart.
It won't. split apart.
It won't split apart because covalent bonds are strong and much stronger than anything pulling on from the hydrogen bonding. But what will happen is it will be attracted. What you're saying is true about the more positive and negative sides, the more positive and negative, the more, again, so all of the kind of hydrogen bonding that I was talking about is going to happen here. This is going to allow this thing to dissolve in water, because when you put it in water, it does this little dance, right? Each of the water molecules are kind of holding hands and hugging each other and letting go and grabbing again. This glucose, which is polar covalent, has the ability to do the same thing. It has more positive sides, which will be attracted to the more negative sides of a water, or more negative sides that are going to be attracted to the more positive sides of a water. So a polar covalent bonded molecule is going to dissolve in water. It doesn't come apart. It's really important to realize it stays intact. Right? We're going to see other cases of things that don't. But a polar covalent molecule will not fall apart. It will stay as an intact glucose, glucose C6H12O6. But it will go and do this dance with all the water molecules with hydrogen bonding and just stay in solution. Uh-huh.
So what you're saying by dissolve is that maybe that one glucose is separating from another glucose?
Yeah, the glucoses will separate from each other and then we'll be just as happy to dance with other water molecules as stay in a crystal of sugar with other sugar molecules.
Okay.
So that makes sense?
Yeah, isn't the general rule that like dissolves like, if I could remember correctly?
Yeah, so we will get there, but yeah. In fact, I'll write that here. Well, it's not going to make sense until we get to what like would, I'll get back to that. But yeah, like dissolves like is an important mnemonic to ultimately, once we get to the end of this discussion. So polar covalent dissolves in water. And again, water is a polar solvent. So that is part of that like dissolves like. Polar things dissolve, polar solutes dissolve in polar solvents. So from that, what happens when we take a non-polar thing like cholesterol or fat or something or oils and try to dissolve them in water?
It does not dissolve.
It does not dissolve. So non-polar molecules do not dissolve. And that's because they don't have any of that charge imbalance to dance with the polar water molecules, right? The water molecules have lots of charged things to grab onto and hold onto. They're just going to ignore anything that's non-polar. Let me add a couple of words. So polar solutes dissolve in water, which is a polar solvent. We say these are hydrophilic, meaning water loving. You know, they like water, which makes sense. They like water. They're making the hydrogen bonds. They're doing that little dance with the water molecules. Non-polar solutes do not dissolve in water. We sometimes say they're hydrophobic. Hydrophobic, which means water fearing, which is not really a good term for it. Again, like the analogy I like to use is, you know, if everybody in like this doesn't work so well when we're all on Zoom because nobody can like hug anybody else. But let's say everybody was in like some big cuddle puddle where everybody is just hugging everybody else, except everybody decided that one, one person, I don't know. I'm looking at, it's a Bonnie, I'm saying your name because you're at the very top corner here. But we've all decided that Bonnie is dead to us. Nobody even, we're going to pretend she doesn't even exist. And everybody else is just going to go in this big group cuddle puddle hug. And she's going to get kind of pushed off to the side, not because we're actually avoiding her, but because we're not even paying attention to her and everyone's just pulling on each other, right? So the water molecules are all pulling on each other, but they are, and so all of the non-polar things just get kind of squeezed off to the side. Right, does that make sense? And yeah,
Or like
Bonnie.
a repellent, they repel.
No,
like-
no, that's what I'm trying to say. They don't repel. They just don't attract. So like if I have all these water molecules that are all kind of pulling on each other and grabbing each other, then these fat molecules or oil molecules just end up getting squeezed out to the side because they're not part of the dance.
Could you use the word inert for this?
No, you use hydrophobic or nonpolar. So this is part of this like dissolves like. There's going to be more to it in a second. But polar solutes dissolve in the polar solvent of water. Non-polar solutes do not dissolve in the non-polar, in the polar solvent, which is water. It is possible to have non-polar solvents, like, gasoline. If you put oil into gasoline, then since the gasoline molecules are non-polar as well, everything just kind of spreads out into a homogeneous way, so it dissolves. What happens if I put sugar in gasoline? If I put a polar solute in a non-polar solvent? If I take here, this is just gasoline, octane or whatever, non-polar molecules, and then I put in my sugar crystal.
It won't dissolve.
It won't dissolve. And why is that?
Because it's a non-polar and a polar. But
And then why can it, but give me more an intuitive sense. So that's true. And why would the sugar start going into solution if that would water instead of gasoline, but not for this non-polar gasoline?
hydrogen bonding, does that
Yeah.
has to do with non-hydrogen bonding?
Well, there is no hydrogen bonding with the gasoline because it's non-polar. So these sugar molecules have this charge imbalance. So they're just going to stay pulled onto their fellow sugar molecules. There's nothing tempting out here. This is like, there's no cuddle puddle to join. With water molecules, there's lots of other things that you can make hydrogen bonds with and go have adventures. But in this case, the sugar just stays intact as a little crystal. I mean, I don't know if it's still a thing. Like when I was a kid, like the nasty thing people would do is like put sugar in somebody's gas tank and get sucked into and be little rocks that would kind of destroy your engine. I think now it doesn't work so well because there's much better filtering and stuff in the gas line. But anyway, this idea of a polar solute in a non-polar solvent, it is not dissolving. It stays as it is. This is going to be really important as we go on through the semester, because some things are polar. A lot of important, like sugar is polar. We're going to see sugar moving around, but there's a lot of things that are non-polar that are important as well, like all the fats, all of your steroid hormones. If we're going to move steroid hormones around in the body, we can't just rely on them to dissolve. We're going to need special carriers and things. If we want to move lipids, fats, and cholesterol from one place to another, we can't just let them dissolve. We're going to have special lipoproteins and structures to move them around. So it's going to actually be really important to pay attention to whether things are polar and non-polar and what the implications are in terms of dissolving in the watery environment of the body or not. And particularly if they're non-polar, we're going to have to come up with other strategies to actually maneuver them around and deal with them. So polar and non-polar is going to be important. Okay, so I'm gonna keep talking just for a little bit since we had the big time with David. So I want to just finish with ionic bonds, which will happen quick. All right, so now we're going to go to ionic bonds. These are where you have something like a sodium, this is a classic table salt, sodium and a chlorine. Chlorine has 7 electrons, sodium only has 1 electron. And instead of sharing electrons, like in the covalent, basically the sodium completely ionizes. The sodium now has no electrons, so now it's Na plus. And the chlorine completely grabs on, so now we have a Cl minus. So these are ions. These are not, this is not two atoms sharing electrons like we saw in covalent bonding. One has completely ionized, one has completely taken up something. So now these are really strongly electrically charged. What's going to happen if you have a really strong plus thing and a really strong negative thing?
They're gonna come together.
Well,
They're going to attract, opposite charges attract. So that's the ionic bond. The thing that's really different though about this compared to covalent, we had like an H2O. These guys, this hydrogen, this oxygen were in it together. They're in their little triad and drifting around, having their adventures, interacting with other molecules, but they stay intact as an H2O. In this case though, this sodium it doesn't know where its ionized electron went. This chlorine, it doesn't know where it got its extra electron from. These sodium and chlorine have no kind of loyalty to each other to be together as a NaCl. So instead, you end up getting this big crystal lattice. You'll end up getting, NAs plus, which then connects to, attracted to the Cl minuses. But then the Cl minuses get attracted to the Na pluses, which are attracted to the Cl minuses. So you end up getting this big crystal lattice. So rather than an intact little NaCl, you actually just have a bunch of Nas and Cls all kind of connected up in this crystal lattice. And this is going to have huge implications for what happens when you take an ionically bonded compound and put it into water. What happens? I'm going to go here. So I have my polar solute, this water here. What happens if I put my salt crystal in here?
becomes electrically charged, conducts electricity.
But more, what happens to let's say this is a salt crystal. This is like just table salt.
Oh.
What happens? So this
It
is,
dissolves.
so it's going to dissolve because it's polar. Na and Cl's have charge, which are going to be able to interact with the polar water molecules. But something more intense than just dissolving is going to happen. Anybody know?
Isn't it like more of like a current or something?
No, but let's stick with the crystal. What happens to the sodium? Does this sodium keep any relationship with the chlorine anymore?
No, it's going to be attracted to the oxygen and water.
Right. So each of these individual ions is going to become its own independent little thing floating around. So this is going to it's going to dissolve, but it's also going to do something more. It's going to dissociate into individual ions. So basically, I'm going to end up having an Na plus doing its own thing. I'll have a Cl minus doing its own thing. Like that Cl minus had no loyalty to any sodium. All it wants to do is kind of dance with positive stuff. I should be on the other side. All it really wants to do is be more on the positive side. So the Cl minuses will be dancing with the more positive sides of the water molecules. The Na pluses are going to be dancing with the more negative sides of the water molecules. So there's no longer such thing as an Na and a Cl anymore while it's dissolved. It's just a bunch of Na pluses and Cl minuses kind of uniformly distributed in the water. So this is important, this word dissociate. It doesn't just dissolve. The actual atoms come apart and become independent.
So is that different than what you were saying about glucose? It remains glucose. Does this not remain?
Exactly. So
Okay.
glucose stayed intact as a individual. Glucose was C6H12O6. When you put it in water, it dissolves, but it stays intact as that entity. When you put a salt crystal in water, there's no longer an NaCl as an intact entity. There's just a bunch of NAs floating around, a bunch of Cls floating around. And that's going to have a huge impact on the osmolarity, which we're going to talk about in the next class. The idea of osmosis is based on how much dissolved stuff. If I have like, 1 mole of if I have 1 mole of sugar or 1 mole of salt, that's the same number of what? Actually, I should mention, we're going to talk about this in a little bit, but what does it mean to be a mole? A lot of people in fact, most people got this wrong on that quiz. Ethan?
I think it's just a number of atoms. It's like 1 times 10 to the 23rd or something like that.
Number of atoms, if it's an element, or number of molecules, if it's a compound. But yeah, exactly. So both of these have, 6 times 10 to the 23rd molecules of this or this. But when you dissolve them in water and you think about how many particles are going to happen, if I look at how many particles in water once we dissolve them, if I dissolve the sugar, we talked about the sugar stays intact. So if I have 1 mole of sugar molecules and I put it in water, since each sugar does not break apart, it stays intact as a intact covalently bonded entity, I'm going to have 1 mole of particles. But if I put 1 mole of sodium chloride in water, this puppy dissociates. It becomes Na plus and Cl minus independently now floating around in the water. So I'm going to actually have 2 moles of particles. This is going to be critical. We're going to talk about this in much more detail, but it's really important. Like if you are trying to calculate what is the appropriate saline solution versus glucose solution to infuse into an IV, you really need to know the difference between glucose and salt in terms of this dissociation and how many particles it turns into, or you're going to end up exploding or shriveling up blood cells once it gets in the body because of the osmotic balance being off. So we're going to spend quite a bit of time in the coming week or this next week talking about osmolarity, osmosis, and why it's so important to keep track of whether something is covalently bonded versus ionically bonded. And typically you can, if something is made with a sodium or a potassium or a lithium or something and a chlorine, typically it's going to be ionically bonded. If it's something from the first or second and the second to last columns of the periodic table, it's typically going to be a ionic bonded, I should say. If it's got, a big carbon like that, it's probably a covalent bond. So any questions? I know we just covered a bunch of stuff, but any questions about this? Cool. So it's 9:55. Let's take a break. Do a slight review. There's a little PowerPoint actually that my colleague Eric Denmeyer actually made up that has some nice graphics that I think will just reinforce what we've just been talking about with prettier pictures. And let me do that. So again, this idea, solutions where you have like some kind of overall thing, which is your solvent, and then the solute, which is the thing that you are putting in there. In this case, in this picture here, what are all these little molecules, these little Mickey Mouses that are supposed to be the solvent?
H2O, water.
That's H2O. And those little white ears are the hydrogens, which are the more positive side. And then the red is supposed to be the oxygen, which is the more negative side. And again, they're all pulling on each other due to what kind of bonds?
Hydrogen.
Hydrogen.
It's all hydrogen bonds there. And the fact that these purple oblong things are in solution here is telling us, is that purple thing probably polar or non-polar?
Non-polar.
If it's dissolved, it's
No?
gonna,
Oh, dissolves is polar.
Polar.
it has to be polar, right? If it was non-polar, then they would all be shoved off on the side and they would not be going into solution.
Okay, can you say that again? It looks like the picture is just, to me, it's like it's non-dissolvable. So can you explain that again?
Right, each of those things is supposed to be like a molecule, say a molecule of sugar. So the fact that each of those things is sitting and dancing with all of the little Mickey Mouses, the little water molecules, means that it must be polar, or else the water molecules would just grab on each other and all of those purple ellipses would all get shoved off to the side. Does that make more sense?
Yes, that makes more sense.
Okay. All right, so homogeneous. Okay, so solvent, solute. And we're going to talk about different kinds of mixtures, solutions, true solutions, and colloids and suspensions. But for right now, let's just keep it simple. In fact, we're going to be looking mainly at where the solvent is a liquid, almost always water, and there's some kind of solute, some molecule in there. We're going to get into this later. So this is showing in a prettier picture what it's like if you dissolve a salt, for instance, like table salt, sodium chloride. In this picture here, we've got this crystal of salt, which is down here at the bottom. The minuses are the Cl minus, for instance. The pluses are the Na plus. And when they're in a crystal of table salt, they're just all connected to each other in this crystal lattice. but then you put it in the water. And once it's in water, like I said, the electrostatic attraction of sodium doesn't care if it's going to a chlorine or to a water molecule. Same thing for the chlorine. The chlorine doesn't care if it's going to a water molecule or a sodium. So each of these ions becomes its own independent little operator floating around in water. And that's why you're going to have, if you consider it like an NaCl as one molecule, you're going to have twice as many independent particles in here because every Na and every Cl is its own independent little thing floating around. And again, we call it dissociation. To dissociate means it doesn't just dissolve. Dissolve would mean it goes into solution, but dissociate means the actual atoms come apart. From what we've talked about, I talked about just electrical current being a flow of charge. Do you think salt water is going to conduct electric current?
Yes.
Yeah, there's lots of free charge floating around in there, lots of pluses, lots of minuses that can just move around and go from one side to another. So that's one of the important properties of these ionically bonded substances. Once they go into solution, is they will conduct electricity. In fact, the word we often use for these salts is we call them electrolytes. I'm drawing with a mouse, so this kind of stinks, but it is coming up on the screen. Electrolytes, because once you dissolve them in water, they conduct electricity. So, let me clear that stuff. So this is kind of showing, just showing once it's all dissolved, it's just all pluses and minuses all in solution. All right, let's continue on here. If you try to, this is supposed to be, there should be a battery in here, but assume there was a battery conducting electricity. Pure water does not really conduct electricity. We're going to see in terms of pH, there is a few charged things, like the water dissociates into H pluses and OH minuses, but at a very low concentration. So for the most part, pure water does not conduct electric current. However, salt water, if you put two wires separated but connected by salt water, the salt water will allow the electric current to flow. And we're going to see this in the lab. Instead of using a bulb in lab, we're going to end up using a buzzer. But that's going to be a way, when we in the lab, part of the lab is testing whether or not a solution conducts electricity. And what we're going to end up doing, again, it's going to be a buzzer. You'll just put the two wires in the solution. You'll dissolve something in something else. We're going to have a whole variety of different solvents and solutes in the lab. And then you put the two wires in and then you listen, does it buzz? If it buzzes, then we can say, oh, it conducts electricity. It's like a really low tech way to check if this solution will conduct electricity. So on Tuesday, that will be part of the procedure that you'll be doing, is actually taking a little electric circuit and putting the wires in the solution and seeing if you hear the buzz. And again, would you expect sugar water to conduct electricity?
No.
No, because each of the sugar molecules, even though it does dissolve, they stay intact as an overall electrically neutral sugar molecule. It doesn't break into individual ions. So there's no individual charges to flow to create an electric current. So, when we're doing, in fact, in our lab, you will be doing this exact thing with salt and with sugar. And again, it's a demonstration lab, so we know what we better find. Like there should not be a surprise here when you do it, but it's kind of just to kind of really convince you that, whoa, this is real. All right, let's continue here. Oh, I got to, oh, there it is. Okay.
If the salt concentration was too low, it wouldn't conduct the light anymore, or it has to be at a certain level of concentration, the salt.
Right. The more salt you have, the more ions you have, the better it's going to be at conducting electricity, for sure. So in fact, if you look here, like in this picture where they have vinegar, vinegar is kind of a weaker electrolyte. There's not as many free charges floating around. That's why he made the bulb look less bright. In fact, we're going to talk about weak versus strong acids and electrolytes in just a moment, because that's going to be important for understanding buffers, which are part of the lab. All right. So again, here, electrolytes such as salt, ionically bonded things, and two super important things to kind of keep track of. Electrolytes, one is they dissociate. So you have individual ions. So we're doubling the number of particles. That's important. Also, since we have free charge, it's going to conduct electricity, and that's also important. Whereas non-electrolytes, something like, again, like glucose, it will dissolve because these are polar molecules. You know, if they were not polar, it would not go into solution. They're polar, but they don't break apart. They do not dissociate. So however many sugars you put in, that's how many particles you've got. And also, since it does not break into individual charges, it won't conduct electricity either. So both are dissolving, both are going into solution, but you know, in kind of some fundamental different properties as well. So similar, and this is something I'll talk a little bit more as well in when we talk about the write-up. You know, part of your write-up will be just describing what you find, but then a big part of it will be interpreting it, you know, putting it into context. So there's things I'm talking about now, like you can see that salt dissolves and sugar dissolves, and they're similar that way, but then you're going to do other tests and find out they're different in other ways, you know. And then in your write-up, you have to kind of explain how your findings fit with what you know about electrolytes versus non-electrolytes. You know, so part of this is going to be doing it to see it, but part of it is also going to be kind of writing up and interpreting your results to make sure that you understand how they connect to the theoretical underpinnings that we're trying to demonstrate. Blah, blah, blah. Clear.
Professor, are these slides going to be available on Canvas?
These aren't, but although there's very similar things in your textbook.
Okay, thank you.
I feel funny putting up since it's not mine officially. But I think it's very similar. We can take a look, but I'm pretty sure in your, in fact, yeah, I can take a look real quick. Oh, we'll look later. All right, so this is important actually to keep in mind. And we'll look at, I'll talk about this in more detail as well. But this idea of just because something dissociates doesn't mean it necessarily goes into total dissociation. I've been talking about the sodium chloride completely all breaking apart. And strong acids also completely all break apart. It's HCl, and every HCl becomes, this is basically an H plus a Cl minus. But there are also weak electrolytes For instance, carbonic acid, which is going to be really important. Or here we have this the HF goes in here, hydrofluoric. It's part of it does break apart. We can see that. Let me get my annotator. We can see that some of these are intact. Some of them are no longer intact. Some of them are where's independent ones. So basically some of them break here. It's basically saying 99% of them don't break apart. Only 1% are breaking apart when it's in equilibrium. So if something is a weak acid or a weak base, it means that it dissociates, but not completely. Either later today or else on Tuesday, I'll talk more about why this is so important for understanding buffers. Like pH buffers are basically weak acids and their conjugate bases. And the fact that these weak acids only dissociate partially is going to be important in how they function to stabilize pH in the solution. So strong acids or strong electrolytes dissociate completely. Pretty much all of the initial thing breaks apart. And I should also mention, this is from a chemistry class. That's why he's saying this is like a hydronium ion. In reality, H pluses don't exist independently. For the purposes of our class, I'm just going to write H plus because it's good enough and it's easier and it'll get all the points we need. But if you're teaching a chemistry class, then you write that. Let's stop this again. Okay, let's stop sharing that. I'm going to now try to answer the other question. Take a look. Actually, here, I'm going to go into share screen. Okay, so this is actually the silverthorn molecular interactions. It's actually worth taking a look here. These are like the sugars, like why is sugar a polar molecule? I can spend just 2 seconds here drawing on this to make it make more sense. Like here's a glucose. When they're in water, they take on this ring form. Whenever you see a hydroxyl hanging off of something, an OH, that's kind of usually a gimme that there is going to be polar stuff going on. Because a hydroxyl is, what is a hydroxyl? It's actually an oxygen, then with a hydrogen hanging off of it. And oxygens are negative compared to the, so this little OH is actually this total polar little deal hanging off there with a negative and positive side that's going to be able to make electrostatic attractions to the water molecules. We also have this oxygen in the ring with its lone pair electrons where we're going to have a preponderance of negative charge. So when you look at any of these like sugars, these are all simple sugars here. The fact that they have hydroxyls hanging off them and the oxygen, it's gonna be pretty clear that it's polar and is going to want to dissolve in water. Like if you're wondering how do we know looking at a sugar molecule that it's polar? It's because there's all these asymmetries between these things that are going to be more negative and more positive. So there's going to be all sorts of local charge imbalance in there. Right, so like part of the lab is going to have you have to go look up a glucose, draw it and show how waters connect to it. But basically, if you have, this hydroxyl hanging off there, which is like an oxygen and a hydrogen, then if I have a water, then I will be able to know that I have, it's kind of, again, you'd use more, oh, wait, it's not drawing. I'm trying to draw it like with little dots. It's not actually making a formal covalent bond, but it's attracted. The more positive part of the water is going to be attracted to that more negative part of the hydroxyl, for instance. So I really want you to kind of start getting this intuition that a polar molecule is going to be attracted to different polar parts of water molecules, and that's why it's dissolving. Also, just reiterate, hydrogen bonds are not that strong. So they are easy to break, which is part of the reason when we look at, again, receptor binding, whether it's a neurotransmitter binding receptors or hormones binding receptors, it's going to be all about, hydrogen bonding and things like that, and it's things that can form, but then get bumped apart and then they break apart. So are questions about what we mean by glucose making hydrogen bonds with water, or why it makes sense that glucose dissolves in water? Okay. Because I can say, but we're going to see in a few moments, a lot of people had trouble with the chemistry review.